Welcome to the chapter on using the formula for short infusions given in a multiple dose schedule. This formula is applicable to the aminoglycosides and vancomycin, particularly when the half-life of the drug is fairly short in the patient. Simpler formulas may be used when the half-life of the drug is long relative to the infusion time of the dose, but it is important to understand when it is appropriate to do so. I have found that the use of this formula is challenging for many students in terms of understanding the various time functions used and considering when concentrations are measured relative to the dose infusion. In this video, we will use estimated pharmacokinetic parameters to predict drug concentrations when doses are administered as short infusions in a multiple dosing scheme. I hope you enjoy the video.
Let's begin with a patient case. A 50-year-old male patient who weighs 100 kilograms with an ideal body weight of 80 kilograms has an estimated creatinine clearance of 68 milliliters per minute. He is to be given gentamicin 160 milligrams every 12 hours as 30-minute infusions. His volume of distribution has been estimated to be 26.4 liters. Predict the steady state peak, which will be drawn 0.5 hours after the end of a dose infusion, and trough, which will be drawn 0.5 hours before the next dose. It's important to note that this is not the true peak and the true trough, which would occur right at the end of the infusion for the peak and right before the next dose for the trough, but rather this allows for time for the dose to be a little late or infused a little late, the phlebotomist to arrive a little early or late, etc., and still have concentrations that are drawn approximately where we desire them to be. First, let's do the calculations. The clearance of aminoglycosides has been found to be approximately equal to creatinine clearance. In our patient, the creatinine clearance was 68 milliliters per minute. However, we want to convert our clearance into liters per hour for ease of calculation. So we're going to multiply 68 milliliters per minute times 0.06. And what that does is convert milliliters per minute to liters per hour. And you can see that this portion, 60 minutes over 1 hour times 1 liter over 1,000 milliliters, would translate to 0.06. When we do that, we find the clearance is equal to 4.08 liters per hour. We know that K is equal to clearance divided by volume of distribution, so our predicted population clearance is 4.08 liters per hour, and our predicted volume of distribution is 26.4 liters. This gives us an elimination rate constant of 0.155 hours to the minus 1 after we cancel out the liters. That translates to a half-life of approximately 4.5 hours. Now let's examine this pictorially. We need the equation that describes the concentration at any time capital T after the end of an infusion lasting T prime time, which is given every tau hours. Here is the equation. Let's look at it pictorially. The concentration at any time capital T after the end of an infusion lasting T prime time given every tau hours. Again, here's the equation. We can see this portion of the curve is the buildup while the infusion is being given. And in this scenario, that equals to T prime time, or the duration of the infusion, which goes in two parts of the equation. Next, once the infusion is ended, the concentration begins to decline. That is the time after the end of the infusion that goes from the end of the infusion time till the next dose is started. That goes into this portion of the equation. Finally, we have the total dosing interval, which goes into the equation right here. This entire portion of the equation is equal to 1 part on the steady state curve, and that's the true peak, right after the end of the infusion. Going from the true peak down the concentration time curve is accomplished by using the e to the minus k capital T portion. So the e to the minus kt is always the fraction remaining of the part that we start with t time later. Once we get down to the end of the dosing interval, we give the infusion again and continue on. So let's consider what the peak and trough would be on 160 milligrams given every 12 hours as 0.5 hour infusions. Here's the equation describing the event with everything filled in except for capital T. If you remember, we're going to give our infusion for 0.5 hours. And then we're going to collect our peak at 0.5 hours after the end of the infusion. Again, this goes in this portion of the curve. Next, we're going to find out the trough concentration, which occurs 0.5 hours before the next dose, which would be at hour 11.5 in this interval. So if we were solving for the concentration at trough, we would be putting in 11 hours into the capital T portion because it occurs 11 hours after the end of the 0.5 hour infusion. Here are the calculations with everything plugged in. Notice for the first part, our time after the end of the infusion is 0.5 hours when we want the peak. And with everything filled in, the calculation comes out for a peak of 6.39 milligrams per liter. For the trough, on the other hand, the time after the end of the infusion when it is drawn is 11 hours, and the trough is 1.26 milligrams per liter. We can also calculate that another way using the formula for the concentration at any time t after an initial concentration Ci. Now C is any concentration that is smaller than Ci, which is always above the C concentration. It's important to note that any concentration above the C would be a Ci. So if I picked one here, it would also be Ci. And if I picked a concentration up here, it would be a Ci compared to this concentration and this concentration. The important part for us is to figure the time between the Ci and the C. And as you can see in this particular scenario, we drew our Ci at a half an hour after a half hour infusion, or 1 hour into the interval. And we drew the C at hour 11.5 just before the next dose. Now finally, let's determine the trough using peak as the Ci. Here's our formula, C equals Ci times e to the minus kt. Our trough concentration is equal to the peak concentration of 6.39 times e to the minus kt with a t of 10.5 hours. And as we've seen before using the calculations with the long formula, the C trough is equal to 1.26 milligrams per liter.